Thanks for the introduction, Miho. I can't believe actually it's been 5 years almost since Solar Orbiter has launched. And so I'm Stephanie Yardley. I'm from Northumbria University in the UK, and today I'm going to talk about solar wind connectivity with Solar Orbiter. And so I'm going to be talking about how we can connect the in situ measurements that we measure at the spacecraft back to their solar wind source regions using the high resolution remote sensing observations also by Solar Orbiter on the Sun. And what I'll be doing is I'll be going from how we plan the observations, how they're planned, how they are executed in the form of these Solar Orbiter observing plans, or SOOPs as we call them, and how the targets are selected. And then I'm going to show some of the results that have come from these solar wind connectivity observation campaigns so far. And so to start, I'm just going to talk briefly, introduce the topic of the solar wind and the sources of the solar wind. And so classically, there exist different types of solar wind, two different types of solar wind. We have the fast solar wind that is roughly above 500 kilometers per second, and then the slow solar wind, which is roughly, again, below 500 kilometers per second. And there is actually a spectrum of solar wind. We do get slow solar wind that does behave like the fast solar wind, but this is classically how we categorize different types of the solar wind. And so the fast solar wind above 500 kilometers per second, the origins are quite well known. And so generally we think that the fast solar wind above 500 kilometers per second comes from these dark patches or dark regions that you can see in the extreme ultraviolet image here from the Solar Dynamics Observatory. And what you'll see here is these dark patches. They're known as coronal holes, and there is these white lines that are on the images, and this is just taken from a magnetic field model to show you where the field lines are closed and open. And so you'll see for this particular region we have these open magnetic field lines associated with these coronal holes, where plasma can easily stream along these open field lines out in the heliosphere as the fast solar wind. Now, with the slow solar wind, the origins are less well known. There are multiple types of origins. And what you can see here is again an extreme ultraviolet map of the Sun, here with source regions of what we think the slow solar wind is overplotted on here. And this is taken using observations from Hinode, where we look at plasma upflowing at the edges of what we call active regions, so these bright regions on the Sun, which is one of the possible areas that the slow solar wind can come from. But it can also come from coronal hole, but this time at the boundaries where we see slower wind speeds, and also potentially maybe coronal holes again, but these low latitude small coronal holes that we get. There's also these coronal helmet streamer structures associated with these active regions on the Sun that are also possible sources. And so there are still some outstanding questions in terms of the origins of the solar wind, and we also would like to know more about how it is heated and accelerated out into the heliosphere. And so there are a lot of questions around the formation mechanisms of the solar wind. And here are just some of the examples of some of the main models that exist to explain how plasma in the corona can escape out as the solar wind. And so we have models that look at the expansion factor. So if we're considering the magnetic field in the corona, and we're thinking about these flux tubes, these open flux tubes on the Sun, then it's been suggested, and we have seen in some cases, that the solar wind speed is inversely proportional to the expansion of these flux tubes. So for example, if you have a small expansion factor, so the what you'd expect from coronal holes where the field is relatively vertical, then you get fast solar wind versus, or on the other side of the coin, where you get the slow solar wind from fields that overexpand, that are largely expanding out into space. And this is all to do with the propagation of waves and how energy is transferred and deposited to accelerate the wind in these kinds of configurations. We have reconnection, which has also been proposed. So how if we get coronal plasma that is along closed field of active regions, escaping at the edges of active regions, like we think with the slow solar wind. Well, this can occur through a mechanism known as reconnection, where the topology of the magnetic field changes, and in particular something known as interchange reconnection, where you have these boundaries between the open and closed magnetic field that you get at the edges of active regions. And then you get this interchange reconnection that can take place and release plasma along the closed field of the active region that's confined in the corona out along open magnetic field out into the heliosphere. And then there's the S-Web model, which is almost like a combination of the two models, where essentially the main explanation is that there are these very narrow channels that we have on the sun. So you can see one in the bottom here. So this dark channel that you can see in the extreme ultraviolet, which map to what we call upflows. So this is measurements of the Doppler velocity, where blue is showing the upflow in plasma. And if these are along open magnetic field lines that radially expand outwards very rapidly, then we can get narrow corridors that transform into these larger open field corridors at higher heights in the corona. So this is just shown in this map here, where the sun is essentially this web of narrow corridors that extend outwards, and also at the edges of these corridors then we can get this interchange reconnection between closed and open field to allow plasma to escape as the solar wind. We've been studying the solar wind for many decades with many different instruments, normally separate remote sensing and in situ instruments on other spacecraft, particularly measuring the variability of the solar wind at 1 AU, say with the ACE spacecraft. However, as the solar wind propagates from the source regions out into the heliosphere, then we often find that the small scale variability of the wind is actually lost at these large distances due to transport processes. And so it's really up to spacecraft such as Parker Solar Probe and Solar Orbiter, which will be my main focus today, that are at closer distances from the sun that can detect this small scale variability. And the bonus of Solar Orbiter is we've got both the remote sensing observations and images of the sun to connect to the in situ measurements out at a closer distance in between the sun and the earth. And so this really allows us to probe the origins of the solar wind and also this small scale variability that we detect in situ, and why we get this small scale variability. And so the way that the Solar Orbiter mission works, the main goal of it is to explore this connection between the sun and the heliosphere using both the remote sensing observations and the in situ measurements. And the way that it works, because of its unique orbit and the combination of instruments and the way that at certain points we can't download as much data due to telemetry constraints in it going behind the sun, then we have these what we call these remote sensing windows. And this is when the high resolution, particularly the partial disk images, take observations at the sun at very high resolution and cadence. And these normally fall within 3 times 10-day windows that occur every 6 months. And so you can see an example plot of Solar Orbiter's orbit during one of these time periods. So you can see the black is this orbit of Solar Orbiter, and you'll notice the coloured, the yellow, brown and blue windows. These are the 3 roughly 10-day remote sensing windows that happen when Solar Orbiter is on its close approach to the sun. And of course, we're looking forward to, which I'll talk briefly later, about the high latitude observations that are coming up as Solar Orbiter inclines its orbit. And so this mission has, as all missions, has these top-level science goals that it wants to answer. And we've seen in the previous webinars these 4 science goals. And so today what I'll be talking about are observations and results from observation campaigns that aim to answer this top-level science goal of what drives the solar wind and where does the coronal magnetic field originate from. And so in order to, it's a long process. We've heard briefly about this in other webinars about how to plan the actual observations, which can take anywhere from about a year to 3 days before the observations. And so what we do is we compose these solar orbiter observing campaigns. We have the timings of the remote sensing windows. So this is what we call the soup kitchen. This is just a tool to help plan what observations are going to be taken, which soups are going to be run, and then what observational studies are going to be run for each instrument. So you can see in the green that we have these 3 remote sensing windows during this particular perihelia. And then we can decide which science goals we're interested in answering and what questions that we want to answer by constructing and basically inserting these soups into the timeline. So you can see these various soups that have been inserted that we've decided that these are the observations that we want to take place. And so this happens on longer timescales, and then closer to the time, medium-term planning, we have these meetings where once we set the science goals and the soups that are going to run, we start to decide on the observational studies that can be run. Of course, we have constraints on telemetry, so we have to run simulations to check that what we're proposing is actually feasible and we can collect the data without, say, overwriting the data. And then once this is all set in stone, closer to the time, we finally have these windows where about 3 days before the observations take place, and this is what these events are referring to here, where we're actually going to point the spacecraft. Are we going to point center or are we going to point pole? Then we have these meetings with ESA and with the operations as SOUP coordinators to essentially choose the target for the SOUP. So are we going to look at an active region? Are we going to look at an active region boundary? And so then once these coordinates are picked and sent to the spacecraft, this is the region that we observe on the sun with the remote sensing observations. And so there have been quite a variety of solar wind related soups. If you want to know more about them, then there's a paper on the soups themselves, and also there's a web page where you can look at the soup summary. And so you can see there's a lot looking at the solar wind and looking at the connectivity as well. And so today I'm just going to focus mainly on the slow solar wind connection campaign, which was first run in March 2022. So when during Solar Orbiter's first close approach, and then I'll finish off with some of the more recent fast wind soup and the observations too. And so, as I mentioned, we have these soups where we design what the science goal and how we're going to answer it using the various observations that we can take with Solar Orbiter. So for this example, we wanted to understand the release mechanisms at these open-closed magnetic field boundaries of the solar wind, where we think this interchange reconnection can take place. And so we had a specific target for this soup, which was either an active region boundary or a coronal hole boundary, where we think the slow solar wind will originate from, and where we'll have these open closed magnetic field boundaries. And so if you set the target, you also then have to take into consideration what observations that you want that will suit this particular target and that will help answer the science goal. And so one of the interesting things about this particular observation campaign is that it depends upon the connectivity of the spacecraft. So what do I actually mean by this? Well, essentially you want to measure the plasma, the solar wind plasma at the spacecraft and then trace this back to its source region on the sun a few days earlier. So the solar wind, depending upon its speed, will take a certain time for it to reach the spacecraft. And so in order to do this, we rely on these magnetic models, or what we call the magnetic connectivity tool, which essentially maps the magnetic field from the spacecraft in interplanetary space down to the corona, to points on the surface of the sun, so we can get an idea of where we want our remote sensing instruments, what target we want to look at. And this can all be done using the connectivity tool, which you can find on this website, that was developed specifically for this particular purpose. And so you can see during the time period in the observations I'm going to show you, you can see the orbit of Solar Orbiter, where we have the 3 remote sensing windows. And so we actually took observations for this SOUP at the beginning of remote sensing window 1, where we're almost along the Sun-Earth line, and then also during this second window as well, when we're slightly closer towards the sun. And then this just gives you in the bottom an idea of the kind of observations that we take. So we have continuous synoptic observations and in situ measurements that are taken, but also then we have these high resolution remote sensing observations and particular studies that are run by the various remote sensing instruments on board. And so this is what target selection looks like. We use a tool called JHelio Viewer. We can import low latency data from Solar Orbiter. So here you can see an EUV image, which was taken by EUI, the Extreme Ultraviolet Imager. And what you'll see on there is the fields of view of the partial disk remote sensing instruments, like EUI, for example, like SPICE. And then also you'll see these connectivity points that we plot at the surface. And so what we can do is we can see what's on the sun at the time, what could be the potential source regions. We can use the connectivity tool to also inform our decision at which location that we point at. And then using JHelio Viewer, we can give the coordinates and the timing of the coordinates to the operations team, and then this gets sent to the spacecraft. So what you'll notice on the right are these are actually the resulting observations that were taken, both the full disk and then the partial disk image by EUI. And you can see also the connectivity points plotted in this region. And so some of the results taken from this particular campaign. So what we can do, as I mentioned before, we can take the remote sensing images of the source and then tie it to the in situ parameters. So here's an example from this particular campaign where we used, I think it was about 6 different instruments on board Solar Orbiter to tie the solar wind plasma back to the sources on the sun. So we can use, as we've already seen, the EUI observations. We have SPICE observations, which tells us about the composition of our source region. This can give us indications of where the solar wind and what region on the sun it originated from, and we can match this with in situ instruments that measure composition as well. And here you can see the probability of these connectivity points. So initially during the time period, we were connected to a corona hole, and then across towards 2 different parts of this active region. And so this is what we were observing at the time. And so we predicted that the solar wind travel time would be about 2 to 3 days. And then what we can do is we can look at the in situ observations and see what we measure in situ. So I won't go through these in detail, but you can use the different instruments such as the solar wind analyzer, the magnetometer. You can look at the electrons distributions on board that Solar Orbiter measures, and you can use this to build a case to where the source regions you're connected to. And so the one example that I will give is actually during this window we detected, if you look at the velocity at the top that is measured by the solar wind analyzer, we see all types of wind from fast, this interesting slow wind that behaves like the fast called the alphonic slow, and the slow wind. And then we can use things like the magnetic field orientation. Does this match the source region that is measured in, does this match the polarity we measured in situ? And we can build up a story of where the solar wind actually comes from. And we did this as well with composition, as I mentioned previously. So we see a certain trend in the composition from photospheric, so from plasma that's come more from the surface of the sun compared to that is contained in the corona inactive regions. And then we can match it to the various composition that we measured on the surface. And so what we did is we saw that the variability that we see in the solar wind is driven by this change in connectivity across the multiple source regions from the coronal hole to the active region. And actually the active region during its time also evolves, which affects what is measured in situ as well. And this is due to this process of the interchange reconnection occurring at the boundaries. And so there have been other studies that have been done from other remote sensing windows. And so this is just if you're particularly interested in these solar wind studies. So during the second remote sensing window, March 2022, we have these two studies here. One looked at a eruption that occurred close to the polar coronal hole. And so we see the dimming. It's similar to a coronal hole, but it has a shorter lifetime that is associated with the eruption, actually merges and becomes part of the polar coronal hole. And so this study looked at the properties of this particular event. We have others, such as one of these corridors that I was talking about earlier, this narrow corridor on the sun. And we see this super radial expansion of this corridor, and it covers about 60 degrees at a distance of about 2.5 solar radii. And so Solar Orbiter was actually detecting very slow wind speeds from this corridor for a period of days. We have new abundance diagnostics, so looking at the composition and matching it from in situ to the source regions at the sun. This was done during the third time we ran the SOUP, so March 2023 this time. And then also we have some instances where we have connectivity on the far side. So the SOUP ran when Solar Orbiter was on the far side of the sun, and so we can't rely on other observatories. It's just Solar Orbiter data that we've got that we're currently analysing. And so then just to finish off, I want to give you an idea of where we've gone. So we ran 4 different studies looking at slow solar wind. We then moved on to a fast wind SOUP, which has run multiple times since. And so this was the first instance it ran in October 2023. And you can see this really nice coronal hole, large coronal hole in the extreme ultraviolet. We had supporting observations from ground base this time as well. And you can see, if you just look at the top panel, that we can see this fast wind coming from what we think is this coronal hole that was observed in the remote sensing images. So this is ongoing work to determine where exactly we think the wind originated from, this coronal hole, and to look at some of the variability that we see in situ. Can we tie this to the source region and variability that happens in the source region too? We can also compare to Parker Solar Probe. So there's certain times when, if you look at this bottom plot, this is the configuration of various spacecraft around the sun, and you can see that these two are Solar Orbiter and Parker Solar Probe. And during a similar time frame, Parker Solar Probe was connected to what we think is the same coronal hole. So you can see very similar signatures in the radial velocity of the solar wind. There was also another run of this SOUP in April 2024. It was very similar in that respect, apart from the fact that Solar Orbiter and Parker Solar Probe are actually radially aligned and very close into the sun. So what I showed previously is this study was about, I think Solar Orbiter and Parker Solar Probe were about 0.6 and 0.4 AU from the sun. This was taken, this study ran during the time period where Parker Solar Probe and Solar Orbiter were at their closest approaches to the sun, and they were also radially aligned. And again, there's a lot of work going into here by these fast wind SOUP coordinators to determine whether the fast wind, or I should say it was a fairly slow fast stream measured by Solar Orbiter, was also indeed measured by Parker Solar Probe as well. And so there are other studies that are currently running, mainly the fast wind soup. I won't show any more, but I will just summarize here. So hopefully I have shown you the importance or how the solar orbiter observing campaigns, particularly to do with the solar wind, run, how we basically build these observation campaigns, how we observe the targets, and then how we analyze and combine all the data sets later on in order to look at the sources of the solar wind and the variability. And there's still a lot of ongoing analysis of these data sets, both with Solar Orbiter and Parker Solar Probe. If you are interested, then please feel free to reach out. And I guess looking forward, it's very close now, is that Solar Orbiter is going to incline its orbit and observe the poles. And so this will begin from March 2025, which is actually next month, where Solar Orbiter will be at an inclination of 17 degrees. Now this will increase year upon year, and so we'll get a very nice view of the poles. And I believe that some of these will have these fast wind soup campaigns that will be running during these periods too. And so here are just the various studies that I showed you. So you can go read about those yourself, or you can ask me any questions now or by email. And I'll stop there.